In an earlier video, we saw how stochastic gradient descent is able to optimize the parameters and hyperparameters of our learning problem. We started with a sinusoidal simple data set, and we introduced during that kind of discussion the mean square error, which was our loss function. As it turns out, mean square error was introduced in a kind of a hand-wavy fashion. Some kind of geometric distance between our predictions and ground truth labels y. But there is quite a little bit of background behind it. So in this kind of section, what we will do is we'll introduce a foundational concept in information theory that was pioneered by Claude Shannon in Bell Laboratories several decades ago, and see ultimately that mean square error can be derived out of this theory, and how this all linked to not only loss functions of regression, but also the loss functions in classification. So I want to introduce the concept of entropy by asking you a question. Imagine that you are a hedge fund manager, and you are someone comes to you with two pieces of information. The first piece of information goes as follows. On a Monday morning, no holidays, just a normal Monday morning, the Holland Tunnel, the inbound direction into the city, will be a parking lot, lots and lots of traffic. And the second piece of information is that in a Monday morning, in inbound again lanes into Manhattan, there will be completely traffic free. No cars will be there. So the question is, which of the two pieces of information would you be willing to bet money on? We will see now which one of the two makes sense for us to select. You have to select one of the two, not both. So most students will respond, I will of course bet money on the high traffic intensity piece of information, because that's what I believe it's going to be true. But as it turns out, the right answer is I will of course bet money on the most unlikely information. And this is the most unlikely event to happen, is that on a Monday morning there actually will be no cars in the inbound traffic into Manhattan. In fact, Claude Shannon put a formula that is actually called the value of information formula, that actually you can see on the screen, and I'll also be writing now in a moment. And this formula is basically says that the value of information about an event, and this event is, let's say, X, is inversely is a log of the inverse of the probability of that event happening. So in the case where we have completely free inbound lanes into Manhattan, this is the probability of that occurring in a Monday morning is very low, and therefore the value of information for that is very high. And there is kind of some form of intuition to remember that, and the intuition is that the value of some information, of any piece of information, is definitely proportional to the surprise, to the degree of surprise that is actually this information is causing us. Why bet money on something that everyone believes that it is so, and therefore everyone accepts as a certainty? So that's the intuition behind this kind of formula, and we'll see now in a moment how this formula is used to define the concept of entropy. So what we have just seen now, let me just write down the equation. So this is the sort of called value of information. Of the event X. And now I think we should go back into the previous experiment that we have seen. We have seen this experiment in while we are reviewing some probabilistic concepts. And in that experiment, it was, if you remember, the Linux FAQ guide experiment, where someone was actually reading the text out of this Linux guide, and the text, the events that we were recording back then were all the lowercase characters of the English alphabet plus the space symbol. The character 27 was a space symbol. And we were effectively counting how frequent each and every of these random 27 random events were occurring, and were quoting the probabilities. We were calculating the probabilities, which of course was a ratio of the number of events that we have observed to the total number of events we have seen in that input text. So on the fourth column over here, what we have done is we have actually taken this I of x formula, and we have quoted for every possible event that value of information. This value of information, as it turns out, is given to us in a familiar to us quantity that is actually called bits. And for those who are just starting to realize the connection with information theory and computer science, there are two ways that you can calculate the value of information. One with the natural log, and in this case it will be given as nuts. And the second is when you use the log 2, which in this case will be the measurement is going to be the very familiar to you quantity called a bit. So going back to that, we have for every possible event that we can meet a corresponding quantity that's actually called bits. The bits you can consider to be very intuitively as the currency, the money, in other words, that we are going to be paying to acquire that kind of information, that random event. And so you can see here that very unlikely characters, such as the character Q, for example, or the character J, in that specific corpus that we have looked at, are carrying a quite significant number of bits, which is the expense that we have to pay to acquire that information. And very frequent characters, such as the space symbol over here, is carrying a very small expense. So the information content of a random event, as we will discuss a bit later, is also present in our daily lives as part of various information compression algorithms that are entirely based on this fundamental principle. Why pay exactly the same number of bits to carry something that it is very frequent, while you can expend far less and carry more number of bits for events which are much less frequent. So what is really entropy? Well, entropy is now introduced as some kind of expectation. In this case, we see here the sample mean of all the information that we have, values of information we have in a probability distribution. And this probability distribution here obviously is discrete. It consists of 27 possible events. Each event has a value of information. We've seen this in bits. And the weight, this weighted sum, is the probability of observing that event. So that formula is fairly intuitive now. And let's try to draw it when we have the case where we have coin tossing. In the coin tossing experiment, we have just a biased coin that we will be tossing, and we will be plotting that entropy and make some kind of easy conclusions now as to how this function looks like. I wrote earlier over here a natural log, but in fact it is log 2, and it's very easy to calculate anything as a base of log 2. So log 2, let's say, of x is log 10 of x divided by log 10 of 2. So any calculator can be used to calculate the log with respect to base 2. Now moving on, let's discuss a little bit about this experiment. In this experiment, we have a biased toying cousin, So we have a bent coin that generates kind of random events. Let's say heads and tails according to some distribution, which we all know is called the Bernoulli distribution. These are all Bernoulli distributed events that we have also seen in a review of probability theory, that type of distribution. And if we are to sort of plot the entropy, which is the degree of uncertainty, carries some kind of degree of uncertainty with respect to our events over here, we will come up with a plot like this. So we will see, we plot this and then plot below it the formula. So this is something like that. So the this plot starts making some sense now. We will introduce why it is shaped the way it is shaped. So if we are to sort of write the equation for that plot, we will write the following. So the entropy h of p is the sum minus the summation over two types of events we have here. Either we have a head or a tails. The probability of this event, and let me just write here a little bit better, this I that belongs to the set heads or tails times log base 2 or 1 minus p of I. Well, that's not entirely correct because the minus is accounted with this minus sign, so this is p of I over here. All right, so let's expand it. This minus the parenthesis of the probability of heads. Let's write this now explicitly. Log 2 probability of heads plus the probability of tails. Well, the probability of tails is 1 minus probability of heads, log 2 of probability of heads. So we'll see this equation again when we are actually discussing binary classification. And if you actually plot it, then over here we have the capital H, and over here we have probability of heads. And we see here the range of the probability of heads evidently between 0 and 1. And when we have probability of heads equal to 0, then everything that we have observed is all tails. This is the sort of what the experiment will result on, all the events. And evidently over here, as you can guess, these are going to be all heads. So coming back to this kind of question about hole and tunnel, now you can kind of get the intuition why pay any money in bits to acquire an almost, actually not almost, it's a certain event of tails. You live in a world that you've never seen anything other than tails, and correspondingly, why pay any money to observe anything in a world of all heads, anything else other than heads? So you will actually, no surprise that the entropy in these two extremes is actually going to 0. It's going to be 0. So, and the maximum entropy is really here at the middle point, and really when the probability of heads is equal 1/2, this is the point where it's the maximum possible point where at that point you have the maximum possible uncertainty as what is coming next. So no surprise that this is going to also be the maximum possible entropy. And any deviation from this point, either to the left or to the right, will have a slightly greater proportion of tails or heads, and then the entropy will actually start to decrease and all the way to 0. So that is a nice kind of diagram to always have in the back of your minds in order for us to connect now this entropy with the loss function, and we'll now see how we do that next. Let's now extend the concept of entropy into what we actually call relative entropy. In entropy, we have one probability distribution. In relative entropy, we have two. So as we can actually see here on the page, we have probability distributions that are involved in this relative entropy formula. which is P of X and Q of X. These are two probability distributions, and we will qualify them shortly when we start now putting some probabilistic notions into the Vapnik block diagram. And as you can see for the formula, the intuition behind this formula is that is also called KL divergence. There are two probability distributions. If these two are very close to each other, in fact on top of each other, then the KL divergence or relative entropy is going to be 0. When they are really far away from each other, the KL divergence is actually a large positive number, or any positive number. In fact, the distributions could be on top of each other, but they could be completely different shapes, as you see in the figure below, and still have a quite significant KL divergence between the two. So treat it in some kind of a probabilistic distance for now, and this distance is going to be very useful to us after we introduce the probabilistic Vapnik block version of the Vapnik block diagram and a very foundational concept called maximum likelihood. This will do next. So let's now put the probability distributions